Hi everyone! So I actually had a lot of videos planned for like sequences and series and sums and induction and combinatorics because those are all topics that are just really interesting to me, and I really wanted to share some interesting properties of them with you. But unfortunately, I decided to leave my notebook at school, which means I don't have any of the scripts here over the weekend, so I'm not going to be able to make any more videos over the weekend, which means that any videos that I do make will have to be on Monday, which means I'll probably not be able to finish all of the videos that I was planning. However, I did want to share with you one interesting property of Pascal's triangle that has to do with combinatorics. And in this video, my focus isn't really going to be explaining combinatorics or Pascal's triangle, so I have explained that in the videos that I planned, which may or may not be made. But otherwise, I'm going to start here assuming that you have already studied both combinatorics and Pascal's triangle. Okay, so just as a review, Pascal's triangle is a triangle of sums of numbers. You start with 1, and then the next row is going to be, also the ends of the row are always going to be 1. One way to imagine this is that there are invisible zeros on either side, stretching out infinitely. So then the next row is going to be 1 plus 0 is 1, 1 plus 0 is 1. The next row is going to be 1, and then you sum the two numbers above it to get 2, and then 1, and then 1. 1 plus 2 is 3, 2 plus 1 is 3, 1, and so on forever. And one interesting property of Pascal's triangle is that each row, this is the 0th row, this is the first row, and then this row is the 0th column, this is a 0th diagonal, this is first diagonal. So each number is actually going to be the row number, choose the diagonal number. And that seems kind of weird, right? Like, you're adding stuff here. What does that have to do with, like, choosing numbers, with combinatorics, which has to do with, like, factorials and multiplication and more multiplication, right? Well, I don't actually know why this happens. I can prove to you that this happens, and in this video we are going to go through an inductive proof of why this is true, but I cannot prove to you exactly why this happens, because the thing about an inductive proof is it shows you that a property is true without really giving any satisfying explanation for, like, why it works. So, but I'm using an inductive proof here because there's some interesting things you can see along the way when you're doing an inductive proof of this. So first I'm going to show you what this looks like. So this row is going to be 0, choose 0. And then that row is going to be 1, choose 0, and then 1, choose 1. And that row is going to be 2, choose 0, 2, choose 1, 2, choose 2, and so on forever. Now, how does an inductive proof work? Well, I like to think of it as like a train, right? You have a train going on a track with infinite stops. But you can't prove that it works for every single stop, because then you would be sitting here working for infinite time, and we don't have infinite time, and also we have better things to do if we had infinite time. Instead, what we're going to do is we're going to prove that the train can land at the first stop. Yes, that is a train, and yes, that is a stop. So we're going to prove that the train can land at the first stop. Then we're going to prove that if the train is at any stop, it can get to the next stop. So then, if we know that it can land at the first stop, we know it can get to the second stop, and we know it can get to the third stop, and so on forever. And then the train can go chugging along happily for the rest of its life. Infinite life. So how does that work in our case? Well, first we have to prove that it can reach the first stop, which in here is going to be the first row. We need to prove that the first row satisfies this combinatorial property. I'm going to call it the combinatorial property because it is a property that has to do with choosing stuff. Maybe I should choose a shorter word. Haha, choose. Okay, I'm going to call it the choose property. So we're going to show that each row of the train has the choose property. So we're going to start with the 0th row. So the 0th row should be 0, choose 0. Now what is 0, choose 0? That looks weird, right? We have a formula of like n factorial, this weird formula with lots of factorials and like multiplication, right? But then what does factorial mean? Well, we define factorial to be a multiplication of the numbers from 1 to n, if we have n factorial. But how do you have a multiplication of the numbers from 1 to 0 when 0 is already less than 1? Well, when we look at factorials, we are actually looking at the number of ways to order n things. Because, like, the number of ways to order 5 cards is going to be 5 factorial. You have 5 options for the first one, 4 options for the second, 3 options for the third, and so on, right? So, how many ways can you order 0 things? Well, you have 0 things, but that doesn't mean there's no way to order them, right? You can say nothing comes first and last, and in the only slot there is. So, there is exactly one way to order 0 things, and that may seem kind of counterintuitive, right? If you're dealing with nothing, but then there's also one way to deal with it. But that's just the way it is, and not only because it sort of makes sense, but also because it fits in mathematically with the rest of the ways that we are using combinatorics. So we have 0 factorial equals 1, and then we also have, which you can prove algebraically from that, or I'm going to prove it sort of separately, or not really prove it, but show it separately, using, like, actually choosing things. So if you have this box, and this box has 8 tops and yo-yos, then if I wanted to choose one thing, right, if I just reached in my hand and grabbed something, then there were 8 options for what I could pick. But if I reach in the box and I grab nothing, then there's exactly one option for what I could pick, and that's nothing. So anything choose 0, the number of ways to choose 0 things is always going to be 1, no matter how many you start with. So anything choose 0 is going to be 1. So that's helpful, because we have here 0 choose 0 as our first row, because this is, or not the first row, as our 0th row, because we know that this is the 0th row in the 0th column, and we said that it's going to be the row number choose the column, or diagonal number. So we just showed that if anything choose 0 is 1, then this works, because 0 choose 0 is 1, and the first row is just 1. So the train stops at the first stop. I'm going to put a check mark here. Train stops at the first stop. So now can we show that the train can go from one stop to the next? Can we show that if we have a row that is working in terms of combinatorics, then we can get the next row in terms of combinatorics? So if we have a row, and I'm going to call it row peace sign. So if we have row peace sign, that's peace sign choose 0, and then peace sign choose 1, and then so on all the way to peace sign choose peace sign, then can we show that the next row in Pascal's triangle will also have this choose property? Well, we can start at the ends, right? Because at the ends we're not really adding stuff. We're adding an imaginary 0, but really we just know that the end is 1. The end here is 1, and the end there is 1. So we already showed that anything choose 0 is 1, which means we can replace this 1 with peace sign plus 1 choose 0. So the first term here satisfies the property, and the last term at the end. If you have some number of items and you want to choose all of them, there's only one way to do that, and that's to take all the items. So the last term is also going to be working because the last term is 1, and that can be replaced by peace sign plus 1 choose peace sign plus 1. But what about the stuff in between? So in between, you are adding the 2 things in the top row, and you are getting something in the bottom row. So for this term here, you would be adding peace sign choose 0 and peace sign choose 1. And this term here, because it's peace sign plus 1 choose 0 to the term after that, you want to show that that equals, so I'm going to make it purple because we don't know it yet. Purple is like a mysterious sort of color, right? So we're going to show that that equals peace sign plus 1 choose 1. And we want to do that for every term in the sequence. So you want to show that, and you can sort of see that this, the number on the right-hand side is going to have the same diagonal number, so it's going to have the same choose number here. And the number on the left-hand side is going to be 1 less. So we're going to show that if you have some number, so if you have the two numbers on top, so that's peace sign choose bow tie, and then peace sign choose bow tie plus 1, then we want to show that that's going to equal peace sign plus 1, because we're in the peace sign plus 1 row, and because we're in the same diagonal as the bow tie plus 1, it has to equal choose bow tie plus 1. So we can show that algebraically, of course, but algebra is kind of boring if you want to explain something, right? It works fine for proofs, but if you want to sort of explain or see how something happens, there's not really much to see when you deal with algebra. But instead, a cool thing about combinatorics is you can usually look at stuff using modeling. So if I have these 8 yo-yos here, right? And yo-yos and tops. And if I want to choose any 3 of them, let's say, then I have 8 choose 3 options. 8 choose 3 options. But what if I care? But what if I want to know how many options have this pink yo-yo? Because I really like this pink yo-yo. So I want to know how many options have this pink yo-yo and how many options don't have the pink yo-yo. Well, we can see that if we have the pink yo-yo, right, then we have 7 yo-yos left, and we still need to choose 2 more. So then, that's going to be, if we have the pink yo-yo, we have 7 choose 2 options. And then what if we don't have the pink yo-yo? Well, then I'm going to take this out. So now we have 7 yo-yos and tops in here, and we still need to choose 3 of them. So that's going to give us 7 choose 3 options. Now, an interesting thing is that in each 3 that you choose, you either have the yo-yo or you don't have the yo-yo, which means that the total options has to be the options where you have the yo-yo plus the options where you don't have the yo-yo. So from that, we know that 8 choose 3 is 7 choose 2 plus 7 choose 3. And we can expand this to like whatever number we want using this. We can see that if we have bow tie, if we have peace sign choose 1 options and we want to choose bow tie choose 1 options from them, then that's the same as if we don't have one of the options, you have peace sign choose bow tie plus 1, and if we do have one of the options, you have peace sign choose the bow tie remaining options that you have to choose. So we have just shown that peace sign choose bow tie plus peace sign choose bow tie plus 1 equals peace sign plus 1 choose bow tie plus 1. And because of that, we know that each number here between the first one and the last one is going to be the sum of the 2 numbers above it, and it's also going to have our choose property. So then we know that if we know that one row has the choose property, we know that the next row has the choose property, which means that if the train is at one stop, then it can reach the next stop. So since we know that it's reached the first stop, we know that at the first row, it has the choose property. Then we know that the second row also has to have the choose property, which means the third row must have it and the fourth row must have it. And note that we still don't know anything about like why the triangle has the choose property. We don't know any intrinsic property of like adding numbers that makes it have this choose property. But what we do know is that because the first row has it, and because we've shown that going from one row to the next, if you have the property, you're going to keep the property, you know that all the rows after that must also have the property. So that's pretty interesting. And it shows a pretty interesting thing about combinatorics, that if you have a combinatorics problem and you want to solve it using algebra, but you don't really have a good idea of what's going on, you can usually find a pretty interesting explanation by actually physically looking at a model of like choosing things and thinking, okay, well, if I'm choosing this many things versus if I'm choosing this many things versus if I'm choosing that many things, and you can sort of come up with a proof from there. So feel free, so you should probably try that out. I don't know if there are any problems relating to proving things using combinatorics in the book, but that's an interesting thing to play around with if you want to try it out. But that's all for now. See you next time!